Good evening and welcome to N-Simplex Pachinko. This is Obi-Wan Pez, your host. And tonight, we're doing a bit shorter of a stream. We're out doing family activities until a bit later this evening. So, yeah, we're doing all right. Just again, for the most part. Busy, busy, busy. You know how it goes. So, alright. If anybody has any questions, let me know, because otherwise, just stick with some random. Hey! Alright, combination of three variables. AXYZ plus BXY plus CXZ plus DYZ plus EX plus FY. Okay, fair enough. Equals 0 for some A through H, yep. Something awful like find the smallest value of X plus Y plus Z. Yeah. So I'm not really sure about a matrix combination because you've got... Right. Yeah, I'm not sure about a matrix combination just because of the ways in which these are mixed. I mean, you could create a vector, but... So if we do this as a vector, do you have a particular combination of... Sorry, let me turn this down a little bit here. Oh, it's already turned down. Okay, cool. I did something like this before. I can't remember what it is now. Yeah, I don't see any of my notes immediately surrounding me, so that's not going to help. I mean, you could do something awful. Nori Alil, welcome. How are you? Let me know if I pronounced your name anywhere near correct. So there, you could do something awful. We could say that we wanted, whoa, X in this direction, Y in this direction, Z in this direction. You're going to have a node where this is YZ, a node where this is XZ, and a node where this is XY, and then one in the middle that's XYZ. Yeah, we're doing all right here. Mostly hanging out, just trying to figure out what else is going on. There we go. So if we're doing this like this, yeah, I don't know any other way to really or I guess you could see this from potentially from the side. You could see this as could be with XYZ in the center. It's a little weird, but that could work. Why, thank you. Do you have any particular questions? Feel free to drop them in chat or otherwise let me know. So yeah, we drew this out like a cube. Did I just drop? No. Okay. That was weird. Right, so if we have something that looks like this, XYZ is in the center. This could be sort of like the planes. We're talking X. Well, yeah, that's a little weird though, because normally you'd talk about the planes in terms of 2 letters, and there are only 3 combinations that you could do, so X, Y, Y, Z, and XZ. So that doesn't quite work. But like, if that one's X, and the one opposite would be like, the one opposite would be the, yeah, YZ. The thing that's missing that one. And these are all going to be adjacents. That's weird. Z. It's going to make this one XY. Oh, interesting. That'd be Y. This would be XC. Yeah. Huh. Trying to make it more understandable, and this thing came out of it. That certainly makes it more interesting. Yeah. I don't think this is going to get me personally anywhere, but... Could make a nice little tetrahedron. So x, y, and z individually would end up being the lower points on a triangle, and each of the individual pairs would be on the faces, and then x, y, z, all of them would be the combination of all of them all the way at the top. I don't have any particular use for this, but could be something. No, that's fair. Got all sorts of equivalent things floating all over the place with the magic squares. Yeah. Makes it interesting anyway. Started on the trig unit for my pre-calc class, so that's always fun. If not impossible to write out in LaTeX. So yeah, in my particular version of this, try to get the students to see the... Yeah, no problem. It always ends up, for some reason, right? I guess it's pretty obvious why, given the random other stuff I've done on this channel. The 3D approach just seems sort of natural, but I think that's kind of one of those things that, like, whatever you've kind of gotten yourself used to, you're just going to kind of do that. So, what I did in my trig class was suggest that the students look at this in terms of, it was kind of funny today. I was just kind of like, how do you find the circumference of a circle? And everybody was talking about, oh, well, circumference is going to be equal to 2 pi times the radius, or pi times the diameter, or whatever. And we got into a little bit of a discussion about certain things about the triangle, and of course 360 comes up. And I was like, so why 360? And they're like, well, because a right angle is 90. And I'm like, no. Hang on. Why is a right angle 90 degrees? And they're like, well, because 4 of them make up. And no, hang on. Y'all are missing the point here. Why 360 and why not like 1? Why isn't the circle just 1? They're like, well, right angles. Like, at some point I was like, okay, no, we're going to have to just bypass all of this. And directly tell you exactly what I'm thinking. Finally, somebody hit on, well, it's pretty close to the number of days in a year. I'm like, you're probably more right than you even imagine. It's the ancient Babylonians were like, oh, well, what should we split the circle up into? Well, being a base 60 number system, sexagesimal, just splitting the circle into 60 parts was nowhere near enough. So they were like, okay, well, maybe let's split it up into the next digit over. And in a base 60 number system, you're looking at 60 to the 0, 60 to the first, and 60 to the second. And we're operating in, again, we're kind of operating this sector saying, okay, what about this? Is it okay to do 160 and no ones? And, well, no, it doesn't really split up nicely. So they're like, all right, maybe if we just move this over a decimal, excuse me, a sexagesimal, maybe this will work. And putting a 1 here makes this 3600 gradations going all the way around. So 3600 ended up being just not good either. Didn't really work in terms of, like, a degree if it was split up into 3,600 parts. Like, that's a lot. And 1 degree of this would be 1/3,600th is barely even registering. So, like, okay, maybe that doesn't work so well. And I'm guessing that somebody did hit on the idea that, oh, well, this is about the same as a year, and 360 is very similar to 3600 in terms of our number system. So looking at it that way, we've got kind of 2 ways that 360 was a much better number. I can't remember who it was who first created the other calendar, but before Caesar's, before any of that. Man, still got a hand of cards stuck in my pocket from earlier. Yeah, I mean, I think so. Because, they wanted to split a circle up, but they also, going way back, right? They would have counted days to figure out when the next time to much closer to reality than you imagine. Yeah, I actually, it was I was doing a probability section in class in one of my other classes. This is the one for liberal arts majors. But I snuck a hand into my pocket, and without anybody really noticing, but they weren't really paying attention to that anyway. And then at some point I reached into my pocket and pulled out the other ones, and they were 4 aces. I'm sure nobody was actually impressed. But, but yeah, we did probability. We're starting on a probability and statistics unit for these people because, you know, they need a lot of it. Hmm. I mean, yeah, definitely, definitely they used 360 well before they knew about the Earth going around the sun. Right? That's definitely true. However, the constellations returning to the same positions in the sky, and when the growing season started, when the first rains or first um, snow, well, not in Babylon, but uh, right when the rainy season started, when certain things happened, when the constellations reached the same places in the sky, that's that's where they would have gotten this. So it's not in terms of, yeah, it's not going to be in terms of the Earth moving a distance because they didn't think that. Yeah, I mean, people had been counting how long that was going to happen since time immemorial. As long as there were people and a cave somewhere to keep track of numbers in, and let's just carve. Um, some of the earliest ones were actually done on wolf bone. There's a Tunguska? No, that's the crater. What's the? Cuba Gamer, how's it going? Czechoslovakia, 1937. Ishango, that was it. Oh no, Ishango was found in Democratic Republic of Congo. Yeah, that was it. There we go. That's from uh, yeah, 20,000. So about 20,000 years ago. So Ishango bone was found in Congo. What's the one that was? The hell's the one from Czechoslovakia? Uh, oh man, Paleolithic era, Czechoslovakia. Oh, that's helpful. So-called wolf bone CS, or Czechoslovakia, Czechoslovakia in Czech. There we go. Oh, dude, I'm sorry. As much as sports drinks suck, right? It's one of those times where one of those would do nicely. Uh, you can also add a little bit of salt to the water. I know it wouldn't taste great, but it's an option. Maybe a little sugar too, just a little tiny bit. Alright, so I don't speak Czech, but it looks to be something like vrči, radius. Yeah, Czech or Czechoslovakian technically because it's old. Um, but the word for wolf in Czech looks a bit, like I said, like vrči. So it's a bone that was found in 1937 that is from a wolf and appears to be forearm radius and looks to be approximately 30,000 years old. And there was one Lebombo, which is a baboon fibula, somewhere in South Africa-ish. That appears to be about 44,000 years old. But the Yashango bone in particular was the first one that had like clear. I think it was that it had clear tally marks, and it wasn't like some of the other ones had notches, but it wasn't like math. I don't remember why Yashango is specifically so much more. Maybe it was just newer. When they find this. When was this found? 1950. Okay, so that's probably why, just because it was sort of new. Wanted to get back into chess and go computers based on previous competitions. Yeah. Adult tourneys. Nice. Yeah. I have certainly not been particularly good at chess in terms of like competitive. I don't think I've never played chess competitively. I played against the I played against our chess club advisor because he and I were colleagues, but like I've never been, yeah, I've never been really into it apart from just playing random games here and there. Never gotten ranked, definitely. I kind of wonder if I could do it. I mean, I can do it, but kind of wonder if I like should try it out now and see, what rank I could get off of it, and or if I could push a different strategy. Because I mean, well, I know. But start pushing the AlphaGo strategy or AlphaZero strategy of just focus on making your pieces have the maximum number of available moves while minimizing your opponent's available moves at the same time, and then start like attacking one square on the board and like really reposition to seriously attack one square. Because I don't know, there were times I was watching that game, or one of the many games, but it was a Stockfish AlphaZero game, the ones that they put online, and I watched it, and there was some moment of clarity that I had where I was just like, what are they doing? it was before I watched the Anna Rudolph breakdowns because I watched her break down all of these things, but I watched one of the games and it moved a knight like that was off off to the left-hand side. It moved it over to the corner and it just left it. And I was like, what is that? And the commentators were saying the same thing. They're like, the hell? What is that? And then yeah. And the commentators are just like, I don't no, that doesn't make any sense. Like, why would it do that? And then 20 moves later or something, it moves the knight into a place where it knocks out a piece and like, two other pieces were already or two other pieces were recently moved somewhere to attack. And then the knight just, casually hops in and takes something. I'm like, whoa. Yeah. Yeah, that's also true. And they did the same thing with Go, with AlphaGo. Um, there was another move where like it just placed a black piece way up in the corner over here, and left it there. And then the commentators again are just like, that doesn't make any sense. And what's who was it? Ah, Lisa Doll. Yeah. So it was when AlphaGo was playing against Lisa Doll, um, Grandmaster, whatever. Whoa, whoa, whoa. All right, cool. That was another, again, moment where it was just kind of like, how how does it even contemplate? And I've played around with some neural networks, so like I know roughly what's sort of happening behind the scenes. Obviously, AlphaGo, AlphaZero are way more complicated than anything I ever touched, but I mean, sort of, but at the same time, like AlphaGo, place that one stone up there, and then like again, 40 some odd moves later, 60 moves later, and this is Go, it like intentionally started pushing the game in that direction. And then suddenly that one piece is a pivotal piece in the entire game. And I'm just like, I don't think it's possible to comprehend this. Well, the other problem with like a deep tactic might be that any one move might end up crushing it. And so maybe it's only going to be a point 0.2 advantage because anything could go wrong to ruin it. But I don't know. It's not like I'm any good. Anyway, so yeah, doing this stuff, I was, trying to get them to think about the unit circle and, oh, 360 degrees, like, it's kind of a useless, not useless, but it's kind of an arbitrary measurement. So, what do we do? Well, if we look at it in terms of the number of radii that we have to wrap around the circle to get to this point, then leaving this as 0 or 2 pi is quite wonderful. So then halfway around the circle is only going to be pi. Half of that is going to be pi over 2. And then we can increment by pi over 2. Well, we increment by pi, we just end up back where we started. Increment by pi over 2, we get 1 pi over 2, 2 pi over 2, 3 pi over 2, and 4 pi over 2. Cut it in half again, get pi over 4, and then increment by pi over 4. So you got 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4. Yes, so I did see Hackenbush. I need to watch the rest of that video. I watched a particular like YouTube introduction to it. That was by some sort of mathematician. I can't remember. He was trying to connect Hackenbush to I can't remember now. It's been a week. But yeah, he was trying to connect it to something, and he was using notation for all of the different moves and like all the different pictures that were made for each one of them. Yeah, yeah. All right, so then like there have only been a few times where I've actually started cursing at the screen like that. One of them was when I found out that my n-simplex research just collapsed into a random walk. Oh! So in the unit circle, I said, okay, we're saying that our radius is just going to be 1 for simplicity's sake. But arbitrarily, without loss of generality, can be defined as any r value you want. And then these are going to be x here and here, because this is a 45, 45, 90, or pi over 4, pi over 4, pi over 2. So these two are going to be equal, and then that means that you've got Pythagorean, x squared plus x squared equals 1, 2x squared equals 1, x squared equals 1/2, and x equals plus or minus root 2 over 2. Or 1 over root 2, which I don't typically shy away from with these particular students. Alright, so then the other one was goodness. What happens if you create a 60-degree angle? Now, again, this normally is placed in this position in standard position, but right now I'm just doing something so that this is separate from that. It's going to be a 60. So one of the ways to write this is you draw in all 6 equilateral triangles, which gets you an inscribed hexagon. And then you say, okay, for each of these, this is now going to be 1/6 of the circle. So pi over 2, or no, sorry, 2 pi over 6 is going to be pi over 3. Each of the radii are 1. And again, since this is pi over 3, and these other two have to be the same, then it's going to make sure that this is also pi over 3 and pi over 3. So we are locked in. Has to be an equilateral triangle even if we weren't trying to make one. So then this is going to split this up into a half, 1, and then here root 3 over 2 is what you get with the Pythagorean theorem. So like y squared plus a half squared equals 1 squared. So y squared equals 1 minus 3, nope, wow. 1 minus a quarter. So y squared is equal to 3/4. And then y, absolute value of y, is equal to root 3 over 2. Exponential, sine, cosine, and everything that follows in analysis. We never really talked about the concept of a circle. It just sort of fell out of the calculations. Oh. Might have to ask you about that one. Alright, so then this also makes that one up here is going to be pi over 6. And pi over 6. Which also means you can reorient the triangle and then get pi over 6 on the side here to just turn the triangle over. The one in our book actually deals with it and says we're going to create a pi over 6 angle here, build an equilateral triangle going down into the negative region as well. I think it might take some stuff for granted. Like the position of the initial side, so the x-axis compared to the triangle that's going around it. We're allowed to use L'Hopital when evaluating the derivative of sin x over x. Yeah, there you go. I got you. I was going to say that's what we know. I mean, that's fine. It's what we did in our class too. All right, so then this means that it's pi over 4. Pi over 4, 5 pi over 4. 7 pi over 4. Right, so then I also tell them then pick these values that are 1/3 the way back over to our axis marks. So this is going to be our pi over 6. And 1 pi over 6 is here. 2 pi over 6 is going to be here, so that's pi over 3. 3 pi over 6 is here, that's pi over 2. 4 pi over 6 is here, that's 2 pi over 3. And 5 pi over 6 is here. 6 pi over 6 is pi. 7 pi over 6 is here. 8 pi over 6 or 4 pi over 3. 5 pi over 3. 10 pi over 6. And 11 pi over 6. Here somewhere. Yeah, but your teacher was happy enough to just let you go on that one. All right, and then I usually insist, oh, let's also just fill in the circle with all of our pi's on 24. That's a pi on 12, sorry. So this is also a thing that I tell the students is that if we'd started just with all increments of pi over 12 and then started just counting up all the way around the circle, this is what we would have gotten to. It's just, why would you have done that? Well, technically, we have no idea why we would have had increments of pi over 12. It would have seemed random. But at this point, now we can see the pattern that exists behind it. It's that all of these special values are going to be all of the simplifiable pi's on 12. I mean, sure, but I don't know any particular values that pi over 5 is going to be equal to. At least all the other ones, pi on 2, 3, 4, 6, and even 12 have, these nice sort of patterns that go with it. Pi on 12 is not particularly nice, but I deal with it. And we're going to, or in our class, we're going to find out later what that's used for. So... But yeah, all the pi's on 12 end up being the values that we can take for all the sums and differences. So, works out nicely. Probably. How can we test it? So we'd have to find some representation for it. It's like the sine of pi over 5 is equal to some sort of I mean, that's not going to work nicely. You can say surely. Construct a use it Pythagorean theorem. Huh. Yeah, okay. All right, touche. I actually just plugged it into the TI-89 that I had laying around, and it is. Sine of pi over 5 is equal to the square root of -2 times root 5 minus 5. That's not a 5. Root 5 minus 5. All divided by 4. Sine of pi over 7 doesn't appear to have a nice one, but that's also... at least not by the same standard. Yes, they're much more prominent in the States, given that they were manufactured here, or at the very least developed here. Yeah, of course they weren't. Of course they weren't manufactured here. That'd be silly. Made in Taiwan. Now, I will say that I'd never owned a TI-89 because it had the computer algebra solver in it. I really wanted one when I was in school, but it was never allowed. You know, the guy who had a 92 had to put it away for exams because it had a computer algebra solver in it. Of course, he was also valedictorian of the next class up, so it's not like he needed the help, but I was fine enough in math anyway that was never an issue for me. I just really wanted a TI-89 because it was really cool. So I finally ended up buying one, I don't know, a couple of years ago, and just like, eBay. Somebody was selling it off for like $50. Like, all right, sounds good to me. Given that new, they are quite expensive. The one that I actually preferred is the 86, because the 86 had all sorts of cool games when I was in high school. And it's an engineering calculator. So like there's all sorts of functions that are in the menus that you have to navigate. Like they'll print the menus on the screen and then you navigate using the buttons. Casio, like I'm sure it can do just about anything that you want it to, but I have absolutely no idea how to work a Casio apart from like the obvious stuff. I mean, realistically, I don't even know the 89 all that well. Like all the menus are just a mystery to me, and when I want to do something specific, I usually have to look it up because it just doesn't help. Just yeah, I missed out on learning the TI-89. It's just not my kind of calculator way back in the day. Yeah, so all of the submenus are basically the same as all TI calculators, but then with the 86 you have the option of being able to, like I said, navigate menus using your F buttons, your function buttons. It still demands rigorous syntax, so you do have to, once you type in the function itself, you do have to manually input all of the arguments to any particular function, which sometimes is annoying, but I think it's worth it. Hmm. Hmm. Yeah. I really like it for all of the, uh, STEM major classes. It really is kind of an engineering calculator. There are some optimizations that make absolutely no sense for anybody but engineers, mathematicians, and physicists. Hmm. Becoming a chemical engineer. Yeah. Or specialist to become. Specialist for. Right. Congratulations. um, hmm. No, I mean, that's fine. And it's different everywhere you go anyway, so even if it's not the title, I probably would never know. Oh yeah, I also looked much more closely at the like graphing of trig functions because I was looking at this and I said, the way that the book, our book introduces it just doesn't make any sense. So if you've got your you're just gonna keep distracting me. All right, so if we get the circle with the axes, you draw a random angle that hits the circle at the point xy. We can drop an altitude, which gets us a right triangle. That distance is x. distance is y, and this distance is 1. Therefore, x squared plus y squared equals 1 is the equation of the circle. We already know that. But to start talking about the trig functions, right, we were looking at, well, here anyway, the stuff inside the circle. The sine of theta is going to be equal to the opposite over the hypotenuse, so y over 1. And then the tangent of theta, and yes, I am skipping, don't worry. Tangent of theta is given by, if we were to use the tangent drawn to the circle. So like we want to know what this length is because that is the tangent length, the length of the tangent on this circle. So if we draw this, this is going to be our tangent of theta. And how do we do this? Oh, well, you can do similar triangles, because here we have a tangent that meets a circle at the end of the radius. Therefore, it has to meet at a 90-degree angle. And then here we've got, like I said, similar triangles. So we've got x to 1. So x here to 1 is the same as y to tangent. So then here, by doing your multiplication thing, tangent of theta is going to be equal to y over x. And then using the same triangle, we've also got another one here, which is a line that runs through 2 points on the outer edge of a circle, which generally speaking, even though it's not necessarily this one, is called a secant. So this specific secant is I know what I want to say. Right, this specific secant is the one that is the radius of the circle. But generally speaking, right, any line that crosses the circle in multiple places is going to be the secant, or is going to be a secant. This particular one just happens to align with the axis. So by similar triangles here with the blue one, we've got, again, 1 goes to secant of theta in the same way that, again, short to long. So here, x to 1. See, this is why I'm here. All right, so then, again, do the multiplication thing. We can get secant by itself is equal to 1 over x, which sine was y over 1. Right, no, I'm coming back to that. Hang on. Secant of theta is 1 over x, and we'll just leave it at that for now. So then there's another triangle here, and I probably want to redraw this because otherwise it's just going to be really messy. So it wasn't just right, this triangle here, it could also have made this triangle here. This is theta, and by opposite interior angles, this is also theta. These are both right angles. They share a side here, so by side angle side, or nope, side angle angle, angle angle side, whatever you want to call it, this is two congruent triangles. So because these angles are congruent, that means that also these angles here are going to be congruent, and they're going to be complementary with theta. So this angle here is pi over 2 minus theta, or we could also just call it something different. So pi over 2 minus theta could just be like alpha. Or leave it as pi over 2 minus alpha. Depends on what we feel like. Then this means that the sine of alpha is going to be our x distance divided by our hypotenuse is 1. But we don't want the sine of alpha. We want this to be in terms of theta. So again, this is the sine of pi over 2 minus theta. Or x over 1, whatever you want to do. But this here is the this is the complement of the original angle, theta. And then when we have the sine of the complement, or the complementary angle, this gets us the complementary sine of theta. So we want the sine of the complementary angle to theta. So that is going to be x. Or x over 1 in this particular case. Okay, we know that from the similar triangles in red, tangent of y, or tangent of theta is y over x, which also means the tangent of theta is going to be our sine that we had here, divided by x is the cosine of theta. All right, then with this diagram, yep. And similarly, if we draw the tangent on the top, the horizontal tangent, this gets us the tangent of the complementary angle, which is the cotangent. And again, by similar triangles, you're saying here cotangent compared to x compared to x is going to be equal to big to small. So in the y direction, right? Big is going to be 1, and small is this y value here. So cotangent of theta is equal to x over y. Or, since we just did it on tangent, this is the cosine of theta over the sine of theta. All right, then what about the other? Cosecant of theta, or the secant of that other angle, pi over 2 minus theta. And again, same stuff, right? So cosecant of theta compared to big to small 1 is equal to, and now we can do y values again. So big to small is going to be 1 compared to y value of this particular object. So cosecant of theta is 1 over y, or 1 over sine theta. Secant. Then you're going to love this. We've just created all of the triangles necessary to figure out all the Pythagorean theorems, or all the Pythagorean identities for trig. So we already had the original, which was radius of 1, horizontal, ended up being the cosine of theta, or just x, and the vertical ended up being just y, or the sine of theta. Again, for the unit circle, if it was not a unit circle and you had a different r value here, that would just be scaled up to both our sine and cosine on the sides. I mean, we hardly ever use secant, cosecant, cotangent. But in reality, the 3 functions that you really need are going to be sine, tangent, and secant. Those are the 3 that fundamentally create everything else and have different behaviors, right? Sine and cosine, they're practically the same thing. Secant and cosecant, cotangent and tangent, they're all the same individual things. They have the same behaviors. They might be a little bit quirky, a little bit different, but all you have to do is like shift it and sometimes flip it, and then you've got the other one. So, all right. So here, sine squared theta plus cosine squared theta equals 1. We also have the larger triangle up in here, which has a, again, has a horizontal value of 1, a vertical value that is the tangent of theta, and a diagonal hypotenuse that is the secant of theta. So 1 plus tangent squared theta is equal to secant squared theta. All right, and then we also have this upside down triangle. Cosecant theta. Up here, cotangent theta. And over here, 1, which means that we got 1 plus, oops, nope, 1 plus cotangent squared theta is going to be equal to cosecant squared theta. All right, give me 1 second here. Yeah, sure, that's pretty neat, meaning but like, yeah, so that's the formulation. You can draw these two these two circles, which then have the complementary triangle and the original triangle and the outside triangle for all three of the and the outside complementary triangle for all of these. Let's see. I always tell my students, like, don't memorize these things, because so many other people, so many other teachers are like, yes, memorize these things. Like, no, don't memorize stuff. Learn how to create it. And eventually it becomes second nature, and it's like memorization, only you know why it exists. And you can, like, corroborate from multiple angles why this thing exists the way it does. And yes, this is correct. Because otherwise, again, it's just arbitrary, and you don't know why. For instance, this is something that I had struggled with for such a long time, was trying to figure out, like, oh, 1 plus tangent squared equals secant squared of theta. Like, is it 1 plus tangent squared, or is it secant squared plus tangent squared, or 1 plus secant squared? Like, I could never figure it out. When I started teaching this, I was still, like, telling my students, I don't remember any of this. So if you just start with it's where you give up and ask Wolfram, no. If you start with this one here, you just say, okay, divide all this stuff by sine squared. And once you do that, you get 1 plus your cotangent squared of theta equals cosecant squared theta. Like, it's just super easy to figure all this out from just sine squared plus cosine squared equals 1, and then that's it. I mean, true, but at the same time, and again, the thing is, like, remembering the formulation or having a visual for it or doing whatever, like something else, doing something across the board might end up creating some sort of connection that you didn't think existed. I mean, this is one of the things that I keep coming back to is that there are other connections that I never knew existed that I keep getting somehow by studying the history of the math, if the math in particular that we're talking about, if I'm studying the context in which people are using it. So, yes and no. Not directly. You have to do a bit of work. So, the sum formula comes from that. Well, I don't want to give a false impression here. So we go like this. We make it two pretty clearly distinct angles. This is alpha. This is beta, which means that the whole thing from here to here is going to be alpha plus beta. Wait. No, that's not what we did. Go back. Hang on. Sorry. That's alpha. That's beta. And this one here is going to be beta minus alpha. I think usually they go the other way around, so that it's alpha minus beta, but whatever, it's fine, it's arbitrary. So we look at the individual locations of these things. And since our x values up top here were cosines of that particular angle, and our y values were sines of that particular angle, again, on the unit circle, it's just r cosine theta, r sine theta. I should do that. The sine of theta is technically equal to y over r, but again, r is equal to 1 for many of the unit circle, or for all unit circles. So we just let sine of theta be y most of the time. Here, again, it doesn't matter whether you include the r's to be generalized or you shrink everything down to, or build everything back up to the unit circle. It doesn't matter. This one over here is, again, the cosine of beta by the sine of beta. All right, then we take the exact same picture. Well, all possible unit circles that you could draw. Right, so take the beta minus alpha that was out here and then tip it back to the axis. So now all that's being done is we just tilt it so that beta minus alpha is going to be starting from the initial side here and then going up like that. This means that this point is going to be the cosine of beta minus alpha by the sine of beta minus alpha. And then this one here is 1, 0. Now the fun part is what happens when you draw this line in. Well, we didn't change it going from one picture to the other. We just changed its orientation. So instead of being up here with a distance d, it is now out here with a distance d. So d squared on the left is going to be equal to, here we create a small right triangle using the endpoints. So cosine beta and cosine alpha have a distance between each other of cosine beta minus cosine alpha. And that distance, the horizontal distance, is going to be squared, plus the vertical distance squared is the sine of beta minus the sine of alpha squared. So that's 1. And the other on this side is going to be that d squared is equal to, here we have in the horizontal direction, cosine of beta minus alpha minus 1 squared. So the distance in the horizontal direction plus distance in the vertical direction is a bit easier. Here we're just dealing with the sine of beta minus alpha as the distance here to 0 is just going to be the same number that we started with. So sine squared parentheses. So then here, if we multiply all this stuff out, keeping d squareds, because if we allow this to work this way, we're going to get cosine squared beta minus 2 cosine alpha cosine beta plus cosine squared alpha plus. Same thing with this one. Sine squared beta minus 2 sine alpha sine beta plus sine of alpha squared, sine squared of alpha, is equal to, now write the right-hand side. It's now going to be cosine squared of beta minus alpha minus 2 cosine of beta minus alpha plus 1 plus sine squared of beta minus alpha. All right, so then, this is the fun bit. Here, we've got cosine squared beta minus alpha plus a sine squared beta minus alpha. So you wanted that. We just want to eliminate that by saying, okay, this is going to end up with a 1 from these because this is a Pythagorean identity. All right, then we've got more. So cosine squared beta plus sine squared beta is going to be 1. And cosine squared alpha plus sine squared alpha. Whoa. It's also going to be a 1. I'm fine, I promise. Oh, man. Maybe it's time to raid. Okay, anyway, we'll finish this out. So now we get 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta is equal to 1 plus 1 is going to be 2 minus 2 cosine beta minus alpha. All right, subtract 2 from both sides. Wanting to do stuff here. Cosine alpha, cosine beta. Or sine alpha, cosine beta. Sine. Sine alpha, sine beta. There we go. Is equal to a negative 2 cosine of beta minus alpha. Divide everything by negative 2. And we get the cosine of alpha times the cosine of beta plus sine alpha sine beta is equal to the cosine of beta minus alpha. So that gets us a nice sum and difference identity. Sum, because you can let alpha be equal to negative beta. All right, so then we get cosine of 2 beta here. So that's going to be cosine of negative beta, cosine of beta, plus sine of negative beta, sine negative beta, sine beta. So then here, cosine of negative beta is an even function, or cosine of beta is an even function. So cosine of negative beta is also the same as cosine of beta. So that's just going to be gone. So this is the cosine squared of beta. And here sine is an odd function, so any negatives on the inside of that will be coming out as well. So we get a minus sine squared of beta. All right, and then if you don't like cosines, we can replace cosine squared with 1 minus sine squared of beta. Or 1 minus 2 sine squared beta. And similarly, again, we can go from cosine squared beta minus sine squared beta. If you don't like sines, we again change this into 1 minus cosine squared beta. . So the cosine of 2 beta is equal to cosine squared beta minus parentheses 1 minus cosine squared beta. So then these two are going to combine because we have a negative 1 that is jumping in. Cosine squared beta minus 1 plus cosine squared beta. So twice cosine squared beta minus 1. Yeah, sorry. It's been a rough kind of day. I've got a lot of exams to correct, and I don't really want to do it. Hope I don't have too many students here. No, I don't have any students here, I'm sure. All right, so let me write it out first to make sure that I have it. So cosine cubed theta times sine theta minus cosine theta sine cubed theta. That one, right? Yeah, okay. So you just take out a sine and a cosine of each. Sine squared theta minus sine squared theta. I got you. That is what we just saw right here. This is cosine of 2 theta. And this right here is 1/2 sine of 2 theta. That was an easy one. Yeah, that's mostly why I do inline. I don't mess around with LaTeX too much. Yep, okay. Yep. Because you have a sine and a cosine. That's going to be 1/4 sine of 4 theta. Right? Yep. All right. All right, now I'm actually going to get out of here because, yeah. Been kind of a rough week, so just busy, not really like bad. Daughter's birthday was this week too, so we had a good time. She's in Scouts, so we ended up, or I made a command level decision. She made a toolbox as part of one of her den activities, so I was like, I'm gonna fill it. So I went out to the hardware store this afternoon and I purchased like, you know, 10 different tools or something like that. The kind of stuff she was going to use anyway. So, multi in one screwdriver, a hammer, measuring tape, uh, you know, combination square that's got a level and a 45-degree, square and a 90-degree square. Uh, so they the leaders were asking like, "Oh, what did you all do this month or whatever?" And so all the kids in her den held up the toolbox, and everybody's like, "Yay!" And they stained everything. They did a really good job, just you know, and I stayed. I mean, I'm at most of her meetings anyway, but you know, my father my father has been a woodworker for a long time, and I never really showed any interest. I was much more into technology, imagine that. So, like, he still had me stand out in his shop learning stuff, regardless of whether or not I wanted to be there. Um, and I must say, I'm grateful for it now, because, I helped her and started showing her, like, how to do stuff. And half of it, I'm like, man, I remember how to. God, I remember going way back how to do some of this stuff. It's just crazy. And, I know the right tool for each job and all this other stuff. And it's, you know, yeah, right. And then she was like, I want to start doing woodworking. I'm like, absolutely. This is a hobby that I can help you with. Even if I don't know how to do stuff, at least I'll know kind of like, the larger scale stuff I can help you out with. And then I may not know how to do something, but also being a mathematician, I can help you figure it out. So it's good times. She's a and she's a great kid, so you know, of course I would say that anyway. All right, so we are gonna raid one Mr. Jason Charles Miller, who is doing his usual music nights. So whatever you want Wednesday he should be there for at least another 20 minutes or so. Let's see how it goes. So Superbrain, Kiwi Gamer Romania, and yes, I will call you out. Hang on, where's the other person? Nori Alil. Thank you all for coming, and anybody else who's out there that was just kind of lurking around, thanks for coming. Makes all the streams very enjoyable. Uh, and yeah, me too. Hopefully. Uh, Hope you all have a good night. So I will be streaming on Friday for more The Forgotten City. And then we'll see next Wednesday where the math takes us. So who knows? More trig. Maybe I'll start talking about the probability and statistics stuff that I'm doing in my other class. Yeah, we'll see how it goes. But anyway, this is Obi-Wan Piss for N Simplex Pachinko. We're going to be rating out in just 10 seconds.